So let's start with the first assignment, linear dependence on functions. The definition is, the functions f1, f2, f3 up to fn are said to be linearly dependent over the interval, closed interval ab. And if there exist scalars alpha1, alpha2, alpha3 up to alpha n, not all 0, such that alpha1 f1x plus alpha2 f2x plus alpha3 f3x up to so on alpha n fnx is equal to 0. So for the functions to be linearly dependent over the closed interval ab, their scalars should not be all 0. Some may be 0, but not all should be 0, right? And on the other hand, if the identity this alpha1 f1x plus alpha2 f2x up to so on alpha n fnx is equal to 0 holds true only for alpha1 equal to alpha2 equal to alpha3 all alpha n equal to 0, which means if all the scalars are 0 for this identity, then the functions are said to be linearly independent functions over the closed interval ab. So remember, for functions to be linearly dependent with this identity, the scalars need not be all 0. And for the functions to be linearly independent, all the scalars should be 0 for this identity, right? Then is the definition for the Wronskian of the functions. You must have listened or heard the word Wronskian. Let's define this. Let f1, f2, f3 up to fn be n functions defined on the interval closed 1 ab. Then the determinant Wronskian of x, which is Wronskian of f1, f2, f3 up to fn. This is defined as taking the determinant of the functions. In the first row, we are having the functions f1x, f2x, f3x up to fnx. And then in the second row, just take the derivative of all of them, the first derivative. Then in the third row, we are having the second derivative for all these functions. Likewise going on, at the last, we will be having the n-1th derivative of all these functions in the last row. Fine. So this is called Wronskian of f1, f2 up to fn over closed interval ab. Now based on this Wronskian of functions, we will be doing some theorems, right? There is a remark. Suppose we are having the number of homogeneous equations. Here it is listed as alpha1 f1x plus alpha2 f2x plus alpha3 f3x is equal to 0, where there are 3 functions, right? And then the second equation is alpha1 f1 dash x with their derivatives, the first derivative, and then third one is taking with the second derivative, the linear combinations, right? Suppose I'm having these 3 as homogeneous equations, then if this system of homogeneous equations has trivial solutions, then determinant of its coefficient matrix is non-zero. Please remember this. This is very, very important for solving the examples. So if the system of homogeneous equation has trivial solutions, then the determinant of the coefficient matrix is non-zero. That is, all the scalars are 0, which means functions are linearly independent. Because for linearly independent, we are having all the scalars to be 0, right? So whenever I'm having trivial solution, which means just take the determinant of the coefficient matrix for these homogeneous equations. Just take the determinant of that matrix. If the determinant comes out to be non-zero, then the system is linearly independent. The functions are linearly independent, right? And if the system has non-trivial solution, non-trivial solutions means not all the alpha i's are 0, not all the scalars are 0, which means the functions are linearly dependent. And for that, the determinant of the coefficient matrix comes out to be 0, right? So whenever you're having the homogeneous equations, take the determinant of the coefficient matrix, check if determinant comes out to be non-zero, then the solution is trivial. And if and trivial means linearly independent. And if the determinant comes out to be 0, then the functions are linearly dependent, right? Next, now while doing the proofs of the theorems or examples, you will understand this more and more clearly. The theorem first is, if the functions f1, f2 up to fn are linearly dependent on the interval that is closed one a to b. What do you mean by a closed interval? Yes, the closed interval. In the closed interval, we are including the points a and b, which means x is greater than equal to a and less than equal to b, right? And if the interval is open, then a and b are excluded, right? The endpoints are excluded. Now the functions are linearly dependent. It is given to us that functions are linearly dependent, which means all the scalars are not 0. Then on the same interval, the determinant of Wronskian of x is identically 0. We need to prove that the determinant of this Wronskian is 0, right? Okay, so given to us that the functions are linearly dependent, which means there exist scalars alpha 1, alpha 2, alpha 3 up to alpha n, not all 0, because for linearly dependent the scalars are not all 0, such that alpha 1 f1x plus alpha 2 f2x plus alpha 3 f3x plus so on alpha n fnx, this is equal to 0 for all x belonging to the given interval AB, which is closed, right? Now to get the Wronskian, I need to find out the derivatives, right? And so I will differentiate this equation or this identity 1 n minus 1th times, right? So let's differentiate this at n minus 1th times. So let me write down first just the identity. Alpha 1 f1x plus alpha 2 f2x plus alpha 3 f3x plus alpha n fnx is equal to 0. Now taking the first derivative, f1 dash x plus alpha 2, because it is a scalar, so this is f2 dash x plus alpha 3 f3 dash x plus alpha n fn dash x is equal to 0. Now taking the second derivative, so this is f1 double dash x, and here it is f2 double dash x, and then f3 double dash x up to so on alpha n fn double dash x is equal to 0. Likewise, just go like this, and at the last taking n minus 1th derivative, so f1 of n minus 1th derivative plus alpha 2 f2 n minus 1th derivative alpha 3 f3 n minus 1th derivative alpha n fn n minus 1th derivative is equal to 0. Let me consider this system of equations to be as 2. These are nothing but the system of the homogeneous equations, right? Okay, now since the homogeneous linear system, this 2 has a non-trivial solution. Why? Because just now in the remark we have read, we have given the functions to be linearly dependent. And when the functions are linearly dependent, which means all the alpha i's are not 0, right? And if all the alpha i's, all the scalars are not 0, which means I'm having the system of equations to be, the solution to be a non-trivial solution, right? Whenever alpha i's are not all 0, we are having the non-trivial solution for these systems of homogeneous equations, right? Now, if we take the coefficient matrix for this system of equations, let's take the coefficient matrix and let's take the determinant of the coefficient matrix. So now taking the determinant as it is written as like this, and for that just take f1x, the coefficient of the scalars, right? So f1x, then f2x, fnx for the first equation, then f1-x, f2-x up to fn-x for the second equation. Likewise, hold the system, this 2 of the system of homogeneous equations, I have taken the coefficients of the scalars and write it down as this, as the determinant of the coefficient matrix. And this determinant, all right. Now, because the system is non-trivial solution, which means the determinant comes out to be 0. Very good. Because we have just read in the remark, for non-trivial solution, for linearly dependent vectors, the determinant is always equal to 0. If the system has non-trivial solution, then determinant of its coefficient matrix is 0. This is the result, right? And this also has another two things, that the scalars are not 0 and the functions are linearly dependent. Linearly dependent, this condition is given to us, right? So the this coefficient matrix, the determinant of this coefficient matrix is 0, which means this is nothing but the definition of the Wronskian. So instead of this, can I write w of x is equal to 0, right? Hence the proof. Second theorem, prove that if the Wronskian of the functions f1, f2 up to fn over closed interval ab is identically 0, then f1, f2, fn are linearly dependent over closed interval ab. This is just the reverse of the previous theorem. In the previous theorem, it is given to us that the functions are linearly dependent, and we have to prove that Wronskian of x is, of these functions are identically 0. Here now it is given to us that Wronskian is given to be equal to 0, and we have to prove that the functions are linearly dependent. Just the reverse of the theorem, right? Proof is also just like the reverse steps. Let's write, suppose let now, because I need that identity, I'm writing that identity for the linearly dependent, for linearly dependent vectors, right? These functions here, these are functions. So I'm writing that identity first, which is taking scalar alpha1 for f1 and alpha2 for f2. So I'm writing the linear combinations. So alpha1 f1x plus alpha2 f2x plus alpha3 f3x plus so on alpha n fnx. So this is equal to 0. This is our identity for all x belonging to the given interval is closed interval AB. Fine. Okay, let me mark this as 1. And now I have to differentiate this n minus 1 at times first, right? So let me differentiate this identity n minus 1 at times. Differentiating 1 n minus 1 at times. So I get, first I'm writing the identity, because I will get the system of homogeneous equations from here. Now taking the first derivative, and then taking the second derivative, so likewise now I'm differentiating this n minus 1th fine. Likewise, just differentiate these. Remember, if the number of functions are n, you have to differentiate up to n minus 1th times. If the number of functions are 3, you have to differentiate up to सिर्फ 2 times, right? Up to 2 times. If the number of functions are 4, then differentiate up to 3 times, just less 1. So this is the system of homogeneous equations and marking as 2. Now since it is given to us that Wronskian of the functions is 0, right? Identically 0, it is given to us, which means the coefficient, what is the Wronskian of the functions? This is the Wronskian of the functions. This determinant is, this is given to be as 0, right? So the system too has, now whenever the, this is the definition for the Wronskian, right? This is the definition for the Wronskian, and it is given that determinant of this Wronskian is 0. This is given to us, right? So I have just written the definition of this Wronskian. On the other hand, whenever, I also knew this, that this is nothing but the coefficient matrix of these system of homogeneous equations. This is also a coefficient matrix of this system of equations. Do you understand? It is given to us that Wronskian is 0. The determinant of Wronskian is 0. Which is clear. Alright, I have written the definition of Wronskians to be equal to 0. But this also implies this is nothing but what? It is also the determinant of the coefficient of the matrix for this system of homogeneous equations, right? So whenever the coefficient matrix of this system of homogeneous equations is 0, this implies what? The system has trivial solution or non-trivial solution? Yes, the system has non-trivial solution, right? So the system too has a, from here I have noticed that the system too has a non-trivial solution, right? Which means all the scalars are not all 0, because for non-trivial solution, scalars are not all 0. Hence, functions f1, f2, fn are linearly dependent, because for linearly dependent, scalars are not all 0, right? So, hence, it is proved that these functions are linearly dependent over closed interval AB, right? Here ends up the proof. Third, prove that if the Wronskian of the functions over closed interval AB does not vanish identically, which means here the determinant of the Wronskian x is not equal to 0. It does not vanish identically, which means the determinant of Wx is non-zero. This is given to us. Then the functions are linearly independent over closed interval AB. Now is the theorem for the linearly independent. And for linearly independent, I need all the scalars to be equal to 0. I must prove that, right? So here I have to prove that the functions are linearly independent. Now I will prove this result by the contradiction, right? I will first suppose that because I need to prove that functions are linearly independent, let's suppose that the functions are linearly dependent, and then I will get the contradiction, right? Okay, so if possible, suppose f1, f2, f3, up to fn are linearly dependent over closed interval AB. So there exist scalars alpha 1, alpha 2, alpha 3 up to alpha n, not all 0. Very good. Such that alpha 1 f1x plus alpha 2 f2x plus alpha 3 f3x up to alpha n fnx is equal to 0 for all x belonging to closed interval AB. This is important to write. Now I am differentiating this n minus 1 times because I need to get Wronskian of the functions. Now for differentiating this n minus 1 time, again I am writing the identity as it is first. Fine. Okay. First, I'm differentiating first as a first derivative, taking the first derivative. Likewise, take the second derivative, third derivative, and I will reach fn dash x. Sorry, here it is, n minus 1th times. Right? So alpha 2 f2 n minus 1th time x. Alpha 3 derivative with n minus 1th times. So I have differentiated this n minus 1th times. Let me mark this as the system of homogeneous equations as 2, complete system as 2. Now since the homogeneous linear system 2 has a non-trivial solution as not all alpha i's are 0, because already we have supposed that these functions are linearly dependent, and linearly dependent means all alpha i's are non-zero, which means the system has non-trivial solution. Remember, non-zero, non-trivial solution, both are having the word non. So, and whenever we have a non-trivial solution, which means the determinant is 0 for all x belonging to closed interval AB. So therefore determinant of Wx is equal to 0, which means taking the Wronskian of this to be equal to 0, right? See, whenever I am having the system of homogeneous linear system, for this system I am having the non-trivial solution, which means if I get the coefficient matrix for this system of equations, right, and taking the determinant of that coefficient matrix, then that determinant is 0. And the determinant of that coefficient matrix of these systems of equations is nothing but the Wronskian, the determinant of the Wronskian x, right? Same definitions. How Wronskian is defined is equal to the coefficient matrix of these system of equations, right? And because it is having the non-trivial solution, which means, okay, I'm writing here this line, which means the determinant of the coefficient matrix of system 2 of homogeneous equations is equal to 0, which means now the line, the determinant of the coefficient matrix of system 2 of homogeneous equations, this determinant of coefficient matrix is nothing but the Wronskian, right? The definition of the Wronskian, it is one and the same thing. So which means the determinant Wx is equal to 0, because the definition of Wx, which is this, and the determinant of the coefficient of those systems of coefficient matrix of those systems of equations is also this same. Wronskian definition is also same this, and the coefficient matrix of all these systems of equations, the determinant is also same. Same thing, right? Because I knew that the determinant of the coefficient matrix of those set of systems of equations is 0, this implies Wronskian is equal to 0. This is a contradiction, right? So Wx is equal to 0. This for all x belonging to closed interval AB, which is a contradiction because it is given to us that Wronskian does not vanish identically. And we have proved here with taking the other possibility, we get the Wronskian to be equal to 0, which is a contradiction. So our supposition was wrong, which means we have supposed wrong that all the functions are linearly dependent, which means all these functions are actually linearly independent, right? So this result is proved with the help of contradiction. Alright, thank you so much for watching this video. We will meet in the next video with examples, right? Okay, thank you.